All right, howdy. Um, so, just to double check, can you guys all hear me? Because I seem to be having an issue with OBS Studio, and this has happened the last few times as well, where my connection is not very good. So, let me know if my voice is like splotchy or like stuff's getting cut out. Okay. Then, today I'm going to talk about the QR decomposition, and then I'm going to get started on the eigenvalues and eigenvectors. So, let's do a review of what we talked about last time. So this was the Graham-Schmidt. Did I spell that right? Yeah. Graham-Schmidt process. So here's what the Graham-Schmidt process takes as input. So you have a basis, x1, x2, x3, all the way through xn for an inner product space, V. And the output is a basis U1 all the way through UN for the same space that is orthonormal. And so let me review what this means practically. It basically means that by taking the inner product of ui with uj, then we get 1 if I is equal to j, and we get 0 otherwise. So it's an algorithm that essentially has this input and this output. And let me remind you guys how it works, because I actually want to do something else with it. So first thing we do is we set u1 equal to x1 divided by the norm of x1. We're just to remind you guys, the norm of x is equal to the square root of the inner product of x with itself. And then we set u2 equal to I guess I'll write it like this. x2 actually, it's somewhat nicer to write it like this. So I'm going to write u2 is equal to x2, and then minus basically what we get when we project x2 onto u1. So we get this. And then over here, if we call this quantity P1, which we did last time, then over here we put the norm of x2 minus P1. And then we keep doing this. And so here we're going to put xk minus pk plus 1, or actually pk minus 1. And then this will be multiplied by uk, and it's going to be set equal to x to the k, and then minus a bunch of stuff, and this stuff is what we're going to call pk minus 1. So let me say what the stuff is again. Basically what we're going to do is we're going to take our vector xk and project it onto all the u's computed previously. So we have xk inner product with u1 times the vector u1 plus xk inner product u2 times the vector u2 plus blah 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 xk inner product uk minus 1, which is the last u computed, times u k minus 1. And so this gives us a list of expressions for the vectors u1, u2, uk, all the way down to the vector un. So this way of computing these vectors u1, u2, uk through un is called the Gram-Schmidt process. And what I now want to do is I want to interpret this process slightly. So here's what we're going to do. We're going to note that we're essentially writing u1 is equal to r1 1 times x1, where in this case r11 is equal to 1 over the magnitude of x1. And we're also writing, actually, let's reorganize this even slightly. I'm going to flip that around, and you'll understand why I'm doing this in a second, but I'm going to instead write x1 is equal to r11 u1, where r11 is equal to the magnitude of x1. And then I'm going to note that my second equality here can be written as x2 is equal to r22 u2 plus r21 u1. And to figure out what r22 and r21 are, we just go back to the previous slide. So in this case, r22 is equal to the magnitude of x2 minus p1, and r21 is equal to the inner product of x2 with u1. So here I was writing down expressions with the thought in my head that I'm going to use these expressions to compute the vectors u1, u2, uk, and you compute them recursively. But now what I'm doing is I'm expressing my original basis vectors, x1, x2, blah, 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 in terms of these new vectors, u1, and then x2 is being expressed as a combination of u2 and u1. And likewise, we can express xk as a linear combination of the vectors u1 through uk. So we're going to put rkk here, and then this is going to be times uk, and then plus rk, and then k minus 1 times uk minus 1, and then plus blah, 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 rk 1 uk. Or actually, sorry, u1. So let me say what all these coefficients are, because we can extract them from the previous slide. So the coefficient here of uk is going to be defined to be this magnitude. In this case, rkk is equal to the magnitude of xk minus pk, and rki is going to be equal to the inner product of xk with ui. So again, we keep doing this, and eventually we get an expression for xn in terms of rnn un plus blah, 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 rn1 u1. So this allows us to express the vectors x1 in terms of the vector u1, the vector r2 in terms of the vectors u2 and u1, and likewise we can express the vector xk in terms of the vector uk through u1. And so as we're doing this version of the Gram-Schmidt process, we're picking up these coefficients, r1, r22, r21, etc. So last time when I introduced the Gram-Schmidt process, I kind of treated these coefficients as a computational artifact, and I didn't really give much attention to them. But now I would like to do that, because it actually leads to something very interesting, and this is known as the QR decomposition. So let's suppose we take the vectors u1, u2, uk, all the way through un, and we treat them as column vectors in a matrix. So what we're going to do is we're going to form a matrix, Q, and this is going to be the matrix where the first column is u1, the second column is u2, the third column is u3, and so on until the last column is un. So now what we can do with this is we can note that there is another matrix we have, and the other matrix we have comes from these R's. So I'm going to actually just write it down explicitly. So the first column of the new matrix R is going to have R11 here, and then 0, 0, 0. The second column is going to have R21, and then R22, 0, blah, 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 0, all the way after that. The third column is going to be R23, or actually, sorry, R21, or R31 rather, R32, R33, and then 0 all the way down. And we keep filling this in this matrix accordingly until we get to Rn1, Rn2, and then blah, 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 blah. We go all the way down to the bottom, and we get Rn. So this is N2. The third column is going to be R31. Actually, did I mess this up slightly? I did, I think. Oh, no, actually I didn't. It's all good. R31 times U1 plus R22 times U2 plus R33 times U3. So I put an X3 here because according to this expression, that's what the product of like R33 with U3 plus R32 with U2 plus R31 with U1. And so likewise, I just kind of keep going, and eventually I get to Xn. So this here is equal to X, where X is the matrix with column vectors drawn from our basis. So this is the QR decomposition of the basis X. I want to say one other thing about it. So not only is R upper triangular, R is also invertible, or I should say non-singular. The reason R is non-singular is the RKK are never zero. The reason they're never zero is precisely because we're going from x1, xn to u1, un. And the only way we can do this is by assuming that these terms right here, in this particular, this is R22, this is RKK, are all non-zero. And if at any point one of these coefficients is zero, we would not be able to solve for UK. So this is the QR decomposition of a basis. Now I'm going to state a theorem that generalizes this. So theorem let A be any M by N matrix of full rank then we can write as Q times R, where Q is an orthogonal M by N matrix, and R is a non-singular upper triangular matrix. So I'll just say how this is proved real quick. So the proof is, since A has full rank, its column vectors form a basis for the column space of A, and we may thus apply the Gram-Schmidt process. To this basis. So really, it's the exact argument we just gave. Okay. So let me do an example of how this is done concretely in practice. I'll start with an easy one. So I'm going to start with a 2x2 example. So let A be equal to the matrix, say 1, -2 for the first column, and 1, 3 for the second. Then what we want to do is we want to compute the QR decomp of A. So first thing we do is we write down our relevant vectors. They're going to correspond to the column vectors of A, so 1 and -2, and 1 and 3. And then we're going to start by computing U1. In fact, we're going to note that 1, -2, this vector, is going to be equal to U1 times R11. And we know that U1 has to be an orthonormal vector, so it has to in particular have length 1. So R11 here is going to be the magnitude of this vector, which you can compute easily to be the square root of 5. And thus, this is going to be R11 times the vector 1 over the square root of 5, -2 over the square root of 5, where this here is U1. The next thing we do is we try to express the vector 1, 3 in terms of U1 and U2. So we're going to have, so the right way to do this is actually to kind of do it the way you would do it in the Gram-Schmidt process. So I'm going to kind of do a little sidebar over here. What I need to compute first off is I need to take my U1 and my x2. In this case, my x2 is this. This was my x1. And then I have to compute the inner product of x2 with u1. And so the inner product of x2 with u1 is going to be equal to 1 over the square root of 5 plus -6 over the square root of 5, because it's 1 times this plus 3 times this, which is just equal to -1 over the square root of 5. And this, of course, is going to be equal to R2 2, 1. So, if you'll recall from our work earlier, what we actually first do is we then look at x2 minus x2 inner product with u1 times u1. This was the thing we were calling, well, this thing right here was the thing we were calling P1. And this ends up being equal to, let's see, 1, 3, minus, in this case, we get minus 1 over 25 in the top component, and we get plus 2 over 25 in the second component, which means this just ends up being equal to 26 over 25 and 73 over 25. So now we know what this quantity is, so we can try to compute its magnitude. And the magnitude of x2 minus x2 inner product with u1 times the vector u1 is going to be equal to, so we're going to have 25 on the outside, and then up here we're going to have square root of 26 squared plus 73 squared. And this right here gives me precisely my R22. And maybe I should compute that real quick, or at least simplify it a little bit. (26 squared plus 73 squared), 6,005. So this is going to be equal to R22 U2 plus R21 U1. We already know what U1 is. We know what R22 is. And so let me go over here and say exactly what U2 should be. Well, what we do is we take the vector we found over here and we divide it by this quantity. So U2 is going to be equal to the vector 26 divided by the square root of 6,005 over 70, or not over, but the second component is going to be 73 divided by the square root of 6,005. So now I have all the data needed for my QR decomposition, and I can write it down. So I'm going to have my matrix Q, and then I'm going to have my matrix R, and the claim is that this should be equal to the matrix 1, -2, and 1, 3. So I go back here, I see my R11 here is the square root of 5. So I put that here. Sorry. I put that here, because this is the R, this is the Q. I put a 0 here. And then I see that my R21 is -1 over the square root of 5. And then I see my R22 is this. So square root of 6005 over 25. And I see my vector u1 here is this. So I go over and I put this in the first column of Q. 1 over the square root of 5 and -2 over the square root of 5. And then my second vector is precisely this u2. So 26 over the square root of 6005. And then let me make sure of something. Yeah. And then 73 over the square root of 6005. And this gives me my QR decomposition. So this right here is an orthogonal matrix. And this right here is upper triangular. And non-singular. Let's do another example. Well, actually, maybe I'll adapt one of the examples I gave last time. So one of the examples I gave last time when I was running the Gram-Schmidt process, this will be example 2, is I considered the list of vectors 1, 1, 1, -1, 4, 4, -1, and 4, -2, 2, 0. And I ran through the Gram-Schmidt process for this, but now I'm going to consider it as basically running through the QR decomposition process for the matrix. 1, 1, 1, -1, 4, 4, -1, and 4, -2, 2. So if you want to remind yourself how this went, you can consult the preceding video. I'm just going to write down the answers I got. I found that if this is x1, this is x2, and this is x3, I found that x1 was equal to R11 times U1, where R11 was equal to the square root of 4, and U11, or U1, was equal to the vector 1, 1, 1, all multiplied by 1 over the square root of 4. And then I found that x2 was equal to R22 or R21 times U1 plus R22 times U2, where, let's see what these were. So R22 was equal to 10 over 4 times the square root of 4, and R21 was equal to 6 over the square root of 4. And u2 was equal to the vector negative 1, 1, 1, negative 1 times 1 over the square root of 4. And I also found that x3 was equal to r31 times u1 plus r32 times u2 plus r33 times u3, where, let's see, r31 was equal to the square root of 4, r32 was equal to negative the square root of 4, and r33 was equal to and r33 was equal to 2 over the square root of 4. And u3 was equal to the vector 1, negative 1, 1, negative 1 times 1 over the square root of 4. So I did all these computations last time when I was executing the Gram-Schmidt process. But now we can interpret them as giving a QR decomposition of the matrix A. So we're going to have a Q and an R, and we're just going to fill out what they should be. So the Q, the first vector of Q, is going to be 1 over the square root of 4, 1 over the square root of 4, 1 over the square root of 4, 1 over the square root of 4. The second is going to be negative 1 over the square root of 4, negative 1 over the square root of 4, or actually, sorry, positive 1, positive 1 over the square root of 4, and negative 1 over the square root of 4. And the last one is 1 over the square root of 4, negative 1 over the square root of 4, positive 1 over the square root of 4, and negative 1 over the square root of 4. And then it's multiplied by the matrix R, which we can now fill in. We know R11 is the square root of 4 here. We know R21 is 6 over the square root of 4. We know R31 is the square root of 4. We know R22 is 10 over 4 times the square root of 4. And we know R2 actually so this would be R23, or actually R32 is negative the square root of 4. And R33 is 2 over the square root of 4. And because R is upper triangular, everything else here is 0. And so this gives us our matrix R, and we know that this is equal to the matrix 1, 1, 1, negative 1, 4, 4, negative 1, and 4, negative 2, 2, 0. So, using our computation from last time, which was just the Gram-Schmidt algorithm applied to this basis, we're able to obtain a QR decomposition of this matrix A. So this is how QR decompositions are calculated. Let's talk about their theoretical significance. So to do this, I'm going to go back to least squares for a minute. So recall the least squares problem. So if a linear system, ax equals b, is not solvable, where x is in Rn and b is in Rm, each equipped with the standard inner products, then find x minimizing the size of the norm of ax minus b. So if we can't find an x that makes this solution be exactly true, instead we try to find the x that minimizes the length between ax and b. And here is the solution. And this assumes A has full column rank. Then what we do is we consider, or actually we have shown that x is just equal to A transpose A inverse times A transpose B. So this is what we proved when we were studying the least squares method or the least squared solution for solving these kinds of problems. And now I want to understand where the QR decomposition fits into this. So let's do a simple case. Suppose Q is an n by m orthogonal matrix consider the least squares problem. Qx is equal to b. Well, according to this solution, we should have that x is equal to Q transpose Q inverse times Q transpose B. Well, here's the nice thing. We proved last time that Q transpose times Q is equal to the identity matrix. So in fact, this whole expression simplifies, and we find that x is just equal to Q transpose times B. So solving the least squares problem is much easier for a matrix that's already orthogonal. But now we can use the QR decomposition to do it more generally. So here's how this goes. Suppose A is a matrix of full rank then we can write A is equal to Q times R. So, to solve the least squares problem, AX equals B, then we simply note that AX equals B is the same thing as QRX equals B. And what we're going to do is we're going to set Rx equal to Y. So this becomes QY is equal to B. And we already know that the solution to this is simply Y is equal to Q transpose B. That's the least square solution. But then we recall that Y is equal to Rx. So we get Rx is equal to Q transpose B. And finally, we find that X is equal to R inverse, because we know that R is invertible, times Q transpose B. So, the QR decomp simplifies solving least square problems, or least squares problems. So let me say why this is. So the geometry of it is kind of beautiful. Let's say right here, this is the column space of A. Then the way least squares works is we have some vector, V. If this is the origin, then we have a vector V pointing from the origin to here. And the way the least squares problem works is that you basically orthogonally project V onto this subspace. And this gives us the projection of V onto R of A. And it turns out to be very, very easy to project a vector onto a space when you have an orthonormal basis for that space. Why? Well, here's what we know. We proved last time that the projection of V onto RA, say RA has an orthonormal basis, U1 through UK, then this projection can be computed very easily in terms of this orthonormal basis, and it just turns out to be the inner product of V with U1 times the vector U1 plus the inner product V with U2 times the vector U2 plus blah, 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 the inner product V with UK times the vector UK. So this right here is exactly how we can compute the projection of this vector onto this space. And it's very, very easy to do when we're using an orthonormal basis for this space. So the reason the QR decomposition formula works so cleanly here in solving least squares problems is because precisely what's happening when you're multiplying B by QR is you're exactly computing this projection. So that's the geometry of what we just did when we solved this equation. So the final question I want to ask, and it's more rhetorical than anything else, is why else are orthogonal bases important? So, here is an amazing fact. And it's, I guess I'll call it kind of a fact, because you need to stipulate some assumptions to make it true on the nose, but I don't really want to get into that. So I'll do it fact with quotations. So amazing fact. The set of continuous functions V on the closed interval from negative pi to pi with f of negative pi equal to f of pi has an orthonormal basis, and I'm going to put this in quotes as well, consisting of the vectors 1 cosine of x, cosine of 2x, blah, 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 cosine of nx, blah, 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 forever, and also sine x, sine of 2x, blah, 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 sine of nx, blah, 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 forever on. So, when I was talking about trigonometric polynomials, I talked about some of these, and I talked about how, for example, with respect to the inner product, 1 over pi, integral from negative pi to pi, f of x, gx, dx. I talked about how, with respect to this inner product, these functions are basically pairwise orthonormal. So unless you you take cosine of x and you integrate it against itself, or sine of x integrated against itself, you integrate it with anything else in this list, according to this inner product, you get 0. So these things are orthonormal, and they form an orthonormal basis in the following sense. Any continuous function on negative pi to pi with f of negative pi equal to f of pi may be written as an infinite sum. And the infinite sum looks something like this. F of x is equal to the sum from I equals, actually, I'll write it like this, A1 plus the sum from I equals 1, or how about A0, from I equals 1 to infinity, of AI cosine of Ix plus Bi sine of Ix. And this right here is called a Fourier series. Now, Fourier series are fairly wonderful for a lot of reasons because they give a lot of different perspectives to the study of calculus. I just want to indicate one of them. And I'm going to do this because it's also going to kind of form a segue into the next topic, namely eigenvalues. So here's what I want to observe about this. I'm going to consider the following operator, D, and it's going to be basically the operator that differentiates a function with respect to x twice. And I'm going to consider what happens when I apply this operator to this function. Then big D of f of x. Well, first off, if I differentiate a constant term twice, I mean, if you differentiate it once, it already goes to 0, so it's going to be 0 plus the sum from I equals 1 to infinity. And now here we're going to have negative, I'm going to differentiate these term by term, so I'm going to have negative I squared and then times AI cosine of x plus b, or cosine of Ix plus Bi times sine of Ix. So note that differentiation kind of preserved the structure of the Fourier series a little bit. The only thing it really changed is it introduced, like when you differentiate cosine of Ix twice, the first time you differentiate it, you get sine of, or I times sine of Ix, and then you differentiate again, you get negative I squared times cosine of Ix. The only thing that changed between this expression and this expression is that the A0 went to 0, and each of the terms in the sum now has a negative I squared next to it. So this is indicative of a behavior that we're now going to name. On the vector space, C negative pi to pi, the function sine, or I should say the functions, sine of kx and cosine of kx are, and I'll explain what this word means in a second, eigenvectors for the linear operator D equals, when you differentiate twice with respect to x, with eigenvalue with eigenvalue negative k squared, whatever an eigenvalue is. And so even without explaining what these words mean yet, you can see the significance of them in this formula. For example, if I was to differentiate twice like a Taylor series, then I would have, so say my Taylor series was AI times xi. After differentiating twice, it would become AI, and then times I, and then times I minus 1, and then times x to the I minus 2. So somehow differentiating Taylor series is kind of messy. The index of the coefficient no longer aligns with the index of the polynomial, and you have to keep count of these different factors that show up. Whereas when you differentiate a Fourier series, the index of the coefficient stays next to the index of the function. And all the changes is you get a little bit of a modified coefficient. So Fourier series are nicer to differentiate than Taylor series. Now, the exact way in which they're nicer to differentiate comes in the notion of an eigenvector and an eigenvalue. And now I'm going to switch topics, and I'm going to start focusing no longer on orthogonal spaces, and more on eigenvectors and eigenvalues. So, yeah. Let me state the key definition. Let L be a linear operator from a vector space V to itself. Suppose that L of x, and actually I'm going to assume that x is non-zero. Suppose that L of x is equal to lambda times x for some x not equal to 0. Then we say that lambda is an eigenvalue of L, and x is an eigenvector with eigenvalue lambda. So this is the fundamental definition. And it kind of is exactly the notion I was trying to indicate in this example on Fourier series. So, here's a question. In fact, I'm going to state multiple questions. So the first question is, how do we find eigenvectors and eigenvalues Another question is, do eigenvalues always exist? And then the third question is, is the association between eigenvectors and eigenvalues unique? So I need to answer all three of these questions. None of them are going to have kind of the exact answer that you would want them to have. But at the very least, there are answers. And so what I'm going to do is I'm going to start with the first question. So, how to find them. So let's write down our equation. Lx, in fact, I'm going to suppose L is represented by a matrix A. And I'm going to consider the equation. Ax equals lambda x. Well, I can rewrite this equation a little bit. First off, I can introduce the identity matrix. So Ax is equal to lambda times the identity matrix times x. And then I can move everything on the right over to the left. And so I would get Ax minus lambda I times x. And then I can factor out the x. And if I factor out the x, I get this equation. So Ax minus lambda I times x is equal to 0. So consequently, x is in the null space I'm sorry, I should have gotten rid of this x here. X is in the null space of the matrix A minus lambda times I. So this actually gives us a recipe to find eigenvectors and eigenvalues. So, how to find them? Part 2. find all lambda such that A minus the identity matrix times lambda is singular. And then 2, for such lambda, find a basis for the null space of A minus I lambda. So we already know how to find null spaces, and we already know how to compute bases. So this part of the problem is at least, I want to say, standard for us. It follows from techniques that we've done in the course already. The first question is something that has a little bit of a novelty to it, but it's also relies on stuff that we've already talked about in this course, because we have an equivalence between A minus I lambda being singular and the determinant of A minus I lambda being equal to 0. So, in some sense, finding the lambda such that this matrix is singular amounts to studying this equation. And this equation is just a polynomial in one variable. Let's do an example to indicate how this works. So I have this matrix A right here, and what I want to do is I want to find eigenvalues and eigenvectors for A. So what I do is I consider the following matrix: A minus the identity matrix times lambda. And this is going to be the same thing as 3 minus lambda, 2, 3, negative 2 minus lambda. And then I compute the determinant of A minus I lambda. And this is going to be the same thing as 3 minus lambda times negative 2 minus lambda, and then minus 6. And so now I can simplify this a little bit. I get lambda squared. And then I get, I believe, minus 1 lambda from expanding this. And I also get minus 6, and then minus 6. So I get lambda squared minus lambda minus 12. And what I'm doing is I'm setting this polynomial equal to 0, because that's the same as setting this determinant equal to 0. So if lambda squared minus lambda minus 12 is equal to 0, this is equivalent to, I believe the factorization here is, or I believe the roots of this polynomial are lambda equals 4 and lambda equals negative 3. Let me sanity check myself on that. Yeah, that's right. So I have these two lambda values, and these two lambda values correspond to this determinant vanishing. So this completes step 1. For step 2, I have to look at each of these lambda values that I found, and I have to find a basis for the null space of A minus I lambda. So what I do is I go down here, first thing I'm going to do is I'm going to look at lambda equals 4. And so in this case, A minus the identity matrix times 4 is going to be the matrix -1 here, 3 here, 2 here, and -6 here. So I must find the null space of this. Let's see how to do that. Well, what I can do is I can basically do row reduction. So I have -1, 2, 3, -6. And what I'm going to do is I'm going to note that I can set row 2 equal to row 2 plus 3 times row 1. And if I do that, I get the matrix -1, 2, 0, 1. So this is a very, I should have 0, 0 down here. So this is a very, very simple row reduction. And I can translate to the linear systems picture, which tells me that -1 times x1 plus 2 times x2 is equal to 0. So this right here corresponds to a bound variable. And this right here corresponds to a free variable. So I find from this that x1 is simply equal to 2x2. And the null space of A minus I4 is going to be equal to the span of vectors 2 and 1. So let's go back up here and let's note that vectors of the form alpha times 2, 1 are eigenvectors with eigenvalue 4. And now the other thing we have to do is we have to consider the eigenvalue -3. So if we look at A minus I times -3, then we're going to get the matrix 6, 3, and here we're going to get 2, 1. So as before, I'm going to go through row reduction first to find the null space. So I do 6, 2, 3, 1. I subtract the first row from the second row. Or actually, I subtract 1/2 the first row from the second row. So row 2 is equal to row 2 minus 1/2 row 1. This gives me 6, 2, 0, 0. And so this right here corresponds to a bound variable. This corresponds to a free variable. And we have that 6x1 plus 2x2 is equal to 0, which means we can express x1 in terms of x2, and we find that x1 is equal to negative 1/3 x2, where x2 is our free variable. So the null space of A minus I times negative 3 is precisely going to be the span of the vectors negative 1/3 and 1. And so now we have found eigenvectors for the eigenvalue negative 3. So vectors of the form beta negative 1/3 1 are eigenvalues, or eigenvectors, with eigenvalue negative 3. And this completes the computation of the eigenvectors and eigenvalues of A. So what's the significance of this? I'll get into this more next time, but I want to state some closing remarks. We can regard two, 1 and negative 1/3 1 as a basis for R2, then the matrix A determines a matrix B with respect to this basis, and B is very easy to write down. Here it's just going to be 4, 0, 0, negative 3. So we talked about before that sometimes linear transformations can look nicer in different bases. And with respect to the basis associated to this eigenvector and this eigenvector, it actually just becomes a diagonal matrix with an eigenvalue 4 and an eigenvalue negative 3. And so this completes our first eigenvalue computation. And next time we'll do a little bit more, and we'll start looking at basically examples that show how powerful the technique of eigenvectors and eigenvalues actually is.